Hi, welcome to this video. I'm Atray from Cosmic Essence, and in this video we'll be discussing the combination of capacitors. Do like this video and share it with your friends. Towards the end of it, I'll also ask you to put down your doubts in the chat box below. So let's get started. So the first thing that we'll be discussing is series combination. Now in series combination of capacitors, two capacitors of same or different capacitance are joined together by the same wire, okay, by the same wire, and of course both the capacitors are joined with a battery, right? This is a battery, and this battery is providing the voltage or potential difference of V. Here the capacitance, say this is C1 and this is C2. Now the interesting thing is that both of these capacitors will have the same charge. Why is that? Because the current that is there, if my this side is say minus Q, right, if my this side is minus Q and this side is plus Q2, right, if I am saying that the two capacitors will have different charges, then let's assume that possibility. I am saying that this side has charge Q2 and this side has charge minus Q. So if this is minus Q, this has to be plus Q because the total charge on a capacitor is always 0, right? Similarly, if this is plus Q2, this has to be minus Q2, right? But now you can see that there is a difference of charge between these two capacitor plates. As that difference evolves, what's going to happen is there will be an internal electric field in this wire because the the charges are not balanced and therefore cancel out. That's why there is a electric field in this wire causing the electrons to move this way, right? And that will only stabilize when both of these plates have the same charge, and that implies that all the plates of capacitors, even of different capacitances, will have the same charge. Okay, very important point, and this is how we prove, okay, not get the formula, but we prove how series combination of capacitors work. So once we understand this, now it becomes very simple. So we see that C1 has charge Q as well as C2 has charge Q, and the total voltage or the potential difference given is V. Now V will be equals to, because this is the total potential difference, it will be equals to V1 plus V2. That is the potential difference across this capacitor as well as this capacitor and the sum of these two. So this V is equals to what? This is essentially Q upon C. This is C equilibrium. Okay, equivalent, sorry, my bad, equivalent, C equivalent, that is when we add both the capacitors, what is the total capacitance, that is what C equivalent is. And here we get Q upon C1 plus Q upon C2 implies we have 1 upon C equivalent as equals to 1 upon C1 plus 1 upon C2. Very simple and straightforward, and this is what the formula, okay, this is what the formula of series combination for capacitors is. But the important thing is, how did we come to this, or the proof of it, okay, what scenario, this understanding of how the how and why the charge on all the plates will be equal is extremely important, right? Now this can obviously be expanded and generalized. This is only for two capacitors, but with the same concept I can generalize it. to say 1 upon C equivalent is equals to 1 upon C1 plus 1 upon C2 plus 1 upon Cn, however many capacitors there may be. Fine. So this is what the series combination is all about. Now let's talk about the parallel combination. Parallel combination is essentially when two capacitors are connected by different wires like this from the same junction, and of course both of them are connected to the same battery. Okay, this is how the parallel plate capacitors is, parallel configuration is. Now let's say this is C1, this is C2. The voltage or the potential difference across both the capacitors is same. Okay, this is a feature and property of parallel combination, that the potential difference across the capacitors or across the wires rather is always same. So this is always V. Okay, so the potential difference across these two junctions is always V for all the parallel configuration. Now that implies that each one of the capacitors have the same potential difference across them. If they have the same potential difference across them, the charge this time will be different. This time the charge across the capacitors will be different, and this is how we are presenting it. Obviously this is the total one. Now the charge, let's say Q upon V, or rather let's say C upon, okay, so Q upon V is equals to C, so let's say Q is equals to C into V. Okay, obviously this C is C equivalent. So now the total Q will be what? Q total will be equals to Q1, that is charge on capacitor 1 and charge on capacitor 2. This is the total Q that will be present on a equivalent capacitor. Okay, what do we mean by equivalent capacitor? If I remove both of these capacitors and put a new capacitor in place of them, then this will be the Q or the charge on that new capacitor, which is equivalent to both of these capacitors. Okay, so that is what we are writing here. So Q total is equals to this. This implies C equivalent into V is equals to C equivalent into V is equals to Q1 is C1 into V plus C2 into V. V cancels out and I am only left with C equivalent is equals to C1 plus C2, and this becomes my formula for parallel configuration of capacitors. Okay, parallel configuration of capacitors. Obviously the same concept can be generalized for any number of capacitors working together. So if I generalize it, C equivalent will be equals to C1 plus C2 plus C3 plus Cn, however many the case. Okay, obviously this is for parallel plate capacitors, right? Okay, so let's take an example to understand the parallel and series configuration and how do we add them all together. So this is the question. The question is essentially, this is a network of capacitors. These three capacitors are in series. As you can see that there is a single wire connecting the three capacitors, and these this and the three capacitors are in parallel configuration. The potential difference across them is 500 volts. Okay, this is the potential difference for the network. The capacitors, each of the capacitors is 10 microfarad, is equal to 10 microfarad in each of them. Now I need to find the C equivalent of the network. That means if I remove all of these capacitors and I put a single capacitor, what would be the capacitance of that single capacitor? That is what I want to find. That is the A part. B part is the charge on each one of the capacitors. So let's get going quickly. Now let's first find A, which is C equivalent of the network. How do we find the C equivalent? First we have to find the C equivalent of this and then we'll parallel it. So first, for the series combination, as we know, the series combination is equals to 1 upon C1 plus 1 upon C2 plus 1 upon C3. So this is my series combination. I know the value of each of them is 10 microfarad, so I'll put 10 in each one of them. So 10, 1 upon 10 plus 1 upon 10 plus 1 upon 10, which obviously equals 3 upon 10. Therefore, C series is equals to 10 by 3 microfarad. Okay, now the C equivalent, because both of them are now parallel, so C series and C4 are parallel, so I will just add C series plus C4 is equals to 10 by 3 plus 10. Okay, so this becomes my total capacitance for the network. Okay, very important result and a very simple result. So this is my answer for part A. Let's now figure out part B. Part B is charge on each of the capacitors. Charge on each of the capacitors. How do we find charge? Charge is simply C into V. Okay, charge is simply C into V. We know the values of C for each of one of them, and I know the potential difference that we are applying to each one of them. So quickly let's find out. For the case of this, Q for all three of them will be same, and so this will be C series into V, which is equals to 10 by 3 into V is 500. Okay, so this becomes my result for charge on all of these. So this is plus Q, this is plus Q, this is plus Q. Okay, so for all of them this is the result, and Q dash I am saying for this is plus Q dash. Why is this different? Because this is in parallel. In parallel configuration, we know that the charges can be different for the capacitors, but in series configuration, all the charges on all the capacitors are always same. So that's why we are doing this. So Q dash is equals to C parallel, which is C 10 into 500, 10 microfarad this is. Okay, and so accordingly the units will come for both of these. That is it. This is how we will solve very simple basic questions of combination of capacitors. If you like this, do like and subscribe to the channel, as well as comment in the comment box below with your doubts and suggestions as to which topics I should be picking up next. I hope to see you in the next video. Goodbye for now.